So what if I told you that we could store every single piece of data ever created by humanity inside a box the size of your shoes? And what if that storage wasn't built in some factory but was actually grown by life itself? Well, today we're diving into the story of DNA as the ultimate hard drive. Okay, let me just start with a statement that sounds like it's straight out of a sci-fi movie, but it's becoming our reality way faster than you think. Humanity is running out of memory. And I don't mean the kind where you can't find your keys. I'm talking about our collective digital memory. You see, we are staring down the barrel of what some people are calling a data apocalypse. And now, this isn't some far-off, distant threat. It's a very real infrastructure crisis that's happening right now. Every photo you upload, every 8K movie you stream, all the data from our smartwatches and smart homes, it's all fueling this digital storm. And our current technology, it's about to be completely overwhelmed. So, where is this data tsunami even coming from? Well, just think about it for a second. We've got these advanced AI models that are learning from datasets that are bigger than any library in human history. We have global sensor networks that are tracking everything from weather patterns to traffic in our cities. Ultra-high-def 8K video is becoming the new standard. And of course, the billions upon billions of connected devices in the Internet of Things, all generating a constant, massive stream of information. The result? We are literally, and I mean literally, at risk of running out of the silicon and the physical space we need to store it all. Okay, so you might be thinking, why can't we just build more data centers? Well, that brings us to a really hard truth about our very best technology. It is shockingly fragile. The problem isn't just about making more space, it's about time. And this right here, this shows the critical weakness in our entire digital foundation. You know, we think of solid-state drives or SSDs as the top of the line, the best storage we've got. And yeah, they're fast for sure. But for long-term archiving, they are fundamentally flawed. Their lifespan is a measly 5 to 10 years. That's it. After that, the electrical charges they used to hold data just start to leak, and your information literally degrades and disappears. For anyone trying to preserve our culture, our science, our history, it is a constant, expensive nightmare of just moving data from dying drives to new ones over and over again. Our digital memory is frighteningly temporary. So if our most advanced, engineered solution is basically built to fail in the long run, where do we even turn? Incredibly, the answer isn't etched on a silicon wafer. It's a biological solution, and it was perfected over 3 billion years of evolution. The solution is DNA storage, and it is exactly what it sounds like. We're talking about taking our digital data, all our ones and zeros, and literally encoding it directly onto synthetic strands of DNA. We are making a fundamental shift from storing information as these fleeting little electrical charges to storing it in the super stable physical structure of life's most essential molecule. Now, I know what you're thinking. That sounds impossibly complex, right? But the science behind it is actually surprisingly elegant. So let's break down how you actually translate computer code into the fundamental code of life itself. The real magic here is in this translation process. You start with your normal binary code, right? The ones and zeros. Then an algorithm basically assigns pairs of those bits to the 4 DNA bases, A, C, G, and T. So for example, 00 might become A, 01 becomes C, and you get the idea. The write process, which is called synthesis, is where a machine uses chemistry to literally build a DNA molecule with that exact sequence, one base at a time. Then to read the data back, you use a DNA sequencer, pretty much the same kind of machine they use in genomics, which figures out the order of the bases. That allows you to just reverse the translation right back into ones and zeros. It's brilliant.
Okay, so we've got the how, but the real question is why? Why go through all this trouble? This is where DNA storage stops being just a scientific curiosity and becomes a technology with absolutely world-changing potential. It really has 2 genuine superpowers.
And that first superpower is information density. And when I say it's mind-blowing, I am not exaggerating. The amount of data you can pack into a tiny physical space is unlike anything else that exists, by orders and orders of magnitude. Just let that sink in for a minute. You could store the entire internet in a shoebox of DNA. Every video, every website, every email, every single scrap of data that makes up our global digital world could fit into a container you can literally hold in your hands. That is the insane power of storing information at a molecular level. Its second superpower? Longevity. And honestly, this chart isn't even a fair fight. An SSD might, if you're lucky, last a decade. But properly stored DNA, it can preserve information for hundreds of thousands of years. I mean, we've successfully read the DNA from woolly mammoths. And, this is the crucial part, It requires zero electricity to maintain. This is the ultimate form of cold storage, data that needs to be archived for the long haul, that you don't need to access every day, but that has to be preserved perfectly for ages without being plugged into anything. So, godlike density and near eternal longevity, I mean, come on, why isn't this technology in your phone right now? This is where we have to come back down to earth and get real about the practical hurdles that are standing between the lab bench and your laptop. So look at this. When you're talking density and longevity, DNA is just in a league of its own. It's godlike. No competition. But then you look at those other rows, and they tell the rest of the story. The speed to write the data, that whole chemical synthesis process, is incredibly slow. And the speed to read it back, with sequencing, also way, way slower than a modern drive. And then there's the big one. The cost per gigabyte is, for now, just astronomically high compared to what we're used to. So here's the deal. The bottleneck isn't the DNA itself. The storage medium is basically perfect. The real challenge is with the machines we have to use to write to it and read from it. The whole global research effort right now is basically a race to make this hardware smaller, faster, and cheaper. But for your everyday files, it's just not practical, at least not yet. And this brings us to the final, really provocative question. What is the future of DNA storage? Is this tech destined to become humanity's ultimate archival vault, preserving our most critical knowledge for millennia, safe from power failures and data rot? Or, as the cost of all this stuff inevitably comes down, could we one day actually see biological hard drives in our everyday devices? The answer to that is going to define not just the future of our data, but how we preserve our entire digital legacy for all the generations to come.